Have you ever wondered how to calculate the volume of complex 3D objects like engine parts or decorative vases? In calculus, we use the washer method. Today, we will master the specific technique of rotating regions around shifted vertical axes using horizontal slices, allowing us to find volumes for shapes with hollow centers. When we rotate a region around a vertical line, we must slice the area horizontally. These slices have a thickness of dy. This means every function we use must be expressed in terms of y. This shift in perspective is the first step to setting up our integral correctly. Before moving to washers, remember the disk method. It calculates the volume of a solid by summing up thin circular disks. Each disk has a volume of pi times the radius squared times the thickness. The washer method simply builds on this by subtracting a smaller inner disk from a larger outer one. Because our slices are horizontal, we need to know the horizontal distance from our axis to our curves. This requires us to ensure our equations are solved for x. If you start with y equals x squared, you must rewrite it as x equals the square root of y to find the radius. A washer is simply a circle with a hole in the middle. To find its area, we take the area of the entire outer circle and subtract the area of the inner empty space. In our calculus problems, these radii will be defined by the distance between our curves and our axis of rotation. The most critical step is defining the radii. The outer radius, capital R of y, is the distance from the axis of rotation to the curve furthest away. The inner radius, lowercase r of y, is the distance from the axis to the curve closer to it. Always measure from the axis, not the origin. When the axis is shifted, for example, to x equals 5, the radius is the difference between the axis value and the function value. If the axis is to the right of the region, the radius is axis minus function. If the axis is to the left, it is function minus axis. Distance must always be positive. Combining these pieces gives us our general formula. The volume is the integral from the lower y bound to the upper y bound of pi times the quantity, outer radius squared minus inner radius squared. We integrate with respect to y because our washers are stacked vertically along the y-axis. Think of the integral as a scanning process. It takes the area of a single washer at height y and adds them all up from the bottom boundary to the top boundary. This infinite sum of infinitesimally thin slices results in the exact total volume of our 3D shape. Let's try an example. We will rotate the region bounded by x equals y squared and x equals y around the vertical line x equals -1. First, we identify our bounds by finding where the curves intersect. Setting y squared equal to y, we find they meet at y equals 0 and y equals 1. Now we find the radii. Since our axis x equals -1 is to the left of our region, we subtract the axis from the curves. The outer curve is x equals y, so r of y is y minus -1, which simplifies to the y plus 1. The inner curve is x equals y squared, so r of y is a y squared plus 1. We plug these into our formula. The volume is pi times the integral from 0 to 1 of y plus 1 squared minus y squared plus 1 squared. Expanding these terms carefully is essential. After subtracting, the constants cancel out, leaving us with a polynomial that is easy to integrate. Applying the power rule, we find the antiderivative. Evaluating from 0 to 1, we get -1/5 minus 1/3 plus 1. Finding a common denominator of 15, we arrive at the final volume of 7 pi over 15 cubic units. This is the exact volume of our rotated solid. Let's look at a case where the axis is to the right of the region. We'll rotate the area between x equals y and x equals 2 around the line x equals 3, from y equals 0 to y equals 2. This changes the order of our subtraction for the radii. Because the axis is at x equals 3, we calculate distance as 3 minus the function. The outer radius reaches all the way to the slanted line x equals y, so r of y is 3 minus y. The inner radius is the distance to the constant line x equals 2, so r of y is 3 minus 2, which is simply 1. Now we set up the integral from y equals 0 to y equals 2. We have pi times the integral of the quantity 3 minus y squared minus 1 squared. Expanding the binomial gives us 9 minus 6y plus y squared. Subtracting the 1 from the inner radius gives us our final integrand, y squared minus 6y plus 8. Integrating and evaluating at the bounds, we find the volume is 20 pi over 3. Notice the shape, it's a cylinder with a cone-shaped hole carved out of the middle. The washer method handled this geometry perfectly by treating the hole as the inner radius subtraction. The method remains the same even with transcendental functions. If you are rotating a logarithmic or exponential curve around a vertical axis, you still solve for x and determine the distance to the axis. The complexity only increases in the integration step, not the conceptual setup. Be careful if the curves intersect within your interval. If the curve that was the outer becomes the inner halfway through, you must split the volume into two separate integrals. Always graph your region first to ensure your outer and inner radii are consistent across the entire range of y. Sometimes the inner radius might be 0 for a portion of the shape. In these cases, the washer effectively becomes a solid disk. You can still use the washer formula, simply let the inner radius equal 0 where the region touches the axis of rotation. The most common mistake is integrating with respect to x for a vertical axis. Remember, if the axis of rotation is vertical, your slices are horizontal. Horizontal slices have thickness of dy. If you use a dx, you are calculating a completely different volume using the shell method instead. Another frequent error is subtracting the functions before squaring them. Mathematically, the square of the difference is not the same as the difference of the squares. You must square the outer radius and the inner radius separately before you subtract them in the integral. Finally, ensure your radii are positive. While squaring a negative radius would technically give the same result, it can lead to confusion in setup. Always think right x value minus left x value to ensure your radius represents a physical distance on the coordinate plane. To wrap up, follow this checklist. First, ensure your functions are in terms of y. Second, find your vertical bounds of integration. Third, identify the outer and inner radii based on the distance from the axis of rotation. Finally, plug them into the washer formula and integrate carefully. Here is a quick check. If we rotate the region between x equals 0 and x equals y squared around the axis x equals 5, which function represents the outer radius? Think about which curve is further from the line x equals 5. The answer is 5 minus 0, or simply 5, because the y-axis is further from the axis of rotation than the parabola is. You now have the tools to calculate volumes of revolution for any region around a shifted vertical axis. With practice, identifying radii and setting up these integrals will become second nature. Keep visualizing the slices, and you'll never get lost. Generated by Vision Solve AI.